Hello students, and welcome to this module about district heating, district cooling and electricity production. This is the fifth module, and we will discuss briefly some system aspects and the distribution. Now, to be able to follow this module, you will have to be familiar with a little bit of fluid dynamics. But have no fear, we will go no further than the Bernoulli equation and the Moody diagram for friction factors. I assume you already have that in some textbook from your undergraduate studies. If you're not if you're not sure about these things, then bring forward your old textbook and refresh your memory a little bit. What you will learn in this module is a little bit about how to set the pressure levels in the system and why the pressures are important, and how the terrain influences the pressure levels, and a little bit about fracturing of the tubes. By the end of this module, you will download a handbook. That handbook will be of great help when it comes to setting up the overall structure and the piping. So the idea with that is to prepare you for the examination task in the next module. To illustrate how to find data for the pressure levels, I have selected at random a fictitious situation in the capital of Peru, Lima. And what I want to do is to demonstrate how web resources like Google Earth can be used as an aid when it comes to this stage in the planning process. Google Earth is available for free and is quite a useful tool when you want to do this kind of overviews. But there are other tools too that offer the same possibilities, and you shall use something you are used to. So I have selected one area, the rectangle, which is assumed to be the heated area, and then I have found an industrial estate where I assume the production plant to be. Generally speaking, you will first want to collect such data that you can compute the total need of heating based maybe on two factors. First, like the area, the number of square meters, and second, the type of buildings on that land. Single-family houses will need some specific amount of heating. Multi-story apartment houses will have another specific demand. And service buildings like shops or offices will be the main third category. So you might need energy signatures for these three categories, or maybe you want to or need to use some other data. You will have to collect these data first. They will differ from country to country and from region to region. And when you have these numbers, you want to have a map so that you can identify different areas and compute the total demands for the different areas. Before we look at Google Earth, I just want to point out that Lima in Peru will not be a good place for a district heating or cooling system. As you can see from this slide, is the daily temperature in Lima a comfortable 20 degrees plus minus 5. So basically you will not need neither heating nor cooling. But that is not important for what I want to say right now. If you've not used Google Earth before, you should try it. It's quite fun. And it's also quite useful. So here we go. I use Google Pro, which is downloaded to my local computer, and what we start with is to say that we want a destination, Lima, Peru, and we click return, and then we fly across the globe to Lima, to the South American west coast, and then we have to zoom in to get the city map reasonably good. And you will notice that we zoom into an area where we have an industrial estate up to the left, and we have this block where I assume we want to deliver heating. You will notice also that a Google map pin is situated inside this area. So the first thing I want to do is to outline the district where I want to deliver the heat and get some data for that. you will notice that now we see the area of this field, which is 4 square kilometers. And then we want to have a look at the distribution distance. So we start from some place in the industrial estate area and we create an orbit, click, 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 down to where we want to have the distribution central in the area. And we see that this is 4.5 kilometers. So now we have the length of the distribution line. But there is one more thing that is very important. So we click set the height profile, and that height profile will then be along the orbit. And now you will see an interesting thing. Now we can trace this orbit from start, and you will notice the red arrow that moves along. So we start from about 113 meters altitude, and it goes up, and there's a little depression here, and up again, and we continue up, and here we are at about 160 meters altitude, and now we continue, and it goes slightly up and down, and here is the end where we have our distribution central. So now let's have a look at what that implies. Now for the example I'm going to go through, I'm reusing an old example and old slides to describe what happens in the distribution system and how the loads and the terrain set the pressure levels. So I will actually not use the height profile we just got from Lima in Peru. I just wanted to show you how to obtain such a terrain profile. The first thing you do is to set up a simple pressure length diagram. So the horizontal axis in this case is the distance from the central production plant. The total length will be about 12 kilometers, 6 forward and 6 back. The vertical axis is the static pressure. We use meters water column or water gauge for this. And you will remember that 10 meters of water column is about equal to 1 bar. You will understand why we use this unit a bit further on. So in the example, does the main distribution pump raise the pressure from 5 to 60 meters, or if you wish, from about 0.5 to 6 bar. As the water passes through the pipes from the pump and back again, will the static pressure drop monotonously. To set up the pressure drops, you would use the Bernoulli equation, and the friction factor will be read from the Moody diagram. So you will basically have, if we limit ourselves to one single tube, a linear pressure loss in the forward pipe from the pump to the last customer. That is the red line. It will really not be exactly linear, because there will be the odd resistances like bends and valves and things, but more or less linear. At the last customer, you will want to add an extra pressure drop, because you want to have an extra margin in the system, and you want to have a reasonable pressure drop over the last customer. So add a 10-meter pressure drop at this point. And then for the return pipe, the blue line in the diagram. The pressure gradient, pascals per meter, is basically the same as for the forward pipe. So you do this for the full load case, and then you will have a first idea of what the pump must deliver. And you will now remember that the pressure drop is proportional to velocity squared. So if we go to half load only by reducing the flow, then will the total pressure drop be reduced to only 25% of that at full load. To avoid too high pump power demand, You will normally select pipe diameters so that the speed of the water in the main distribution pipes is no higher than some 4 to 5 meters per second. That is for the main, the thickest, the biggest pipes. They can be anything from 500 to 1500 millimeters in diameter. The pipes extending to individual customers may be as thin as some 20 to 25 millimeters. And in these thin pipes you want the water to travel slower. You would really want to add a curve for the minimum load case, but for my examples I have chosen to use half load 50%. Now will you understand why we use meters as the measure for pressure, meters of water column? Because now we can add the terrain curve in the same diagram as we have the pressures, and that is the thick green line. In Lima we had a terrain height curve starting at 113 meters, peaking at 160 and then dropping off again with a few depressions along the way. In the slide we start at 0. There is a depression and a hill, and then it drops off again. So set the reference height at 0 in the plant itself, and then we plot the relative height in the diagram. As I said before, are these slides old, so the green line is not the profile from Lima, but you will understand the idea. Now you must realize that the actual terrain height is the opposite to the terrain pressure influence. At an 8-meter depression, will the static pressure become 8 meters higher than it was at the reference level? And on the hill, 20 meters high, will the actual pressure become 20 meters lower? So if the green curve is higher than the static pressure curve, will there be a negative static pressure in the pipe? And that may not happen. To avoid steam formation in the pipes, and hence blocking, we must now guarantee that the static pressure, as calculated by the Bernoulli equation, is always higher than the pressure reduction because of the height differences. Boiling, caused because the pressure drops below the saturation steam pressure, is known as cavitation. Once the pressure again rises above the threshold, will the steam bubbles formed suddenly collapse? This causes local pressure waves that may be disastrous. So cavitation must be avoided. And that is what I have done here. You will observe that I added an extra 10 meters as a margin. At a distribution temperature of 110 degrees, will a boiling limit of 10 meters water gauge correspond to a temperature margin about 15 degrees Celsius. So the distance between the thick green line and the dashed line is a safety measure, equivalent to approximately 15 degrees temperature increase in the district heating water. Now to find the dimensioning strength of the pipes will again the terrain have a pronounced influence. In this case, what you do is to set the terrain height profile to just touch the highest pressure line as computed by the Bernoulli equation, and then you read the intercept value on the pressure axis. So we now have everything to construct a diagram that shows how the static pressure in the main pipe will change all along its length. But there will also be dynamic effects to take into account. Pressure waves may well occur depending on several factors, and pressure waves can be severe. Let's just do an oversimplified treatment in which we assume a completely rigid tube in which water is flowing at 3 meters per second. The tube is 300 meters long and has a cross-section of 1 square meter. So what will be the force we have to apply to bring this mass of water to a full stop? And since we know the cross-section, we will transfer that to a pressure. Since the tube is completely rigid, we have to estimate the breaking distance by aid of data for water. In most cases, do we consider water an incompressible fluid? But really it is not. At 100 bars is the volume of water actually compressed, and the volume is about 0.1% smaller than at 1 bar. So if we just assume that the pressure becomes 100 bar and we have a volume reduction at 0.1%, then will the total water volume experience a reduction in length equal to 0.3 meters. The center of gravity will travel only half that distance, so it will travel 0.15 meters, and that is then the breaking distance. Since the velocity drops from 3 meters per second to a standstill, is the mean velocity 1.5 meters per second. So the time becomes 0.1 seconds. And then the acceleration becomes the mean velocity 1.5 meters per second divided by the time 0.1 seconds, which is equal to 15 meters per second squared. The result does not fit with the original assumption that the pressure would become 100 bars, and there are several other oversimplifications in this treatment. But the only thing I wanted to show with this was the most simplified picture of how a pressure wave can be created. Now in 1900 did Nikolai Zhukovsky from Russia publish an equation for the amplitude of pressure waves arising from sudden blockages or momentum changes in pipe flows. This very simple equation gives a much better estimate than what we did on the previous slide. So delta P is quite obviously the result, the sought amplitude. Rho is the density. For water we can use 1000 kilos per meter cube. The density is temperature dependent, but for the moment we can ignore that. U sub sound is the sound velocity in the medium. In free water, like a lake or the sea, it exceeds 1400 meters per second, but in an enclosed volume like a pipe is the velocity depending on a lot of parameters such as the pipe diameter. It is also temperature dependent. But for estimates we can use 1400 meters per second. In case you want to learn more about the pressure wave velocities, I'd recommend the paper mentioned in this slide. It's freely available on the web, so just search for it. Now delta U bar is the change in velocity, so that will be 3 meters per second in our case. Finally, the Zhukovsky formula gives, in this case, basically the same result as the extremely simple treatment on the previous slide. The reason that the sound velocity appears in the equation is that the pressure wave will start bouncing back and forth in the pipe while being damped. Count on 5 to 10 bounces before it has dissipated. But the fact that the sound velocity appears means that the occurrence of the pressure shocks has something to do with time. If the pressure wave bounces back and forth between the ends A and B of a pipe that is L meters long, then will the time for the shock wave to go from A to B and come back to A again become the total length traveled divided by the velocity. Changes in the water momentum, like velocity changes, shall never ever be faster than this time constant. Assume that the closing time for the valve is several times longer than the time constant. Then, when the initial pressure shock comes back to the valve is still partly open. So the overpressure may escape. And then again, when the second bounce comes back, the valve is still part open. So first, by the slow closing, is the amplitude reduced, and then is the overpressure allowed to escape successively. So that is why. Another possible cause of sudden pressure shocks is cavitation, as mentioned previously. Cavitation means that steam bubbles form in a low pressure zone. And when the pressure is increased again, then these bubbles will implode, they will collapse. And that will cause shock waves, pressure waves, as the water rushes in to fill the cavity that was previously full of steam. So not only flow blockages but also cavitation are risks from local low pressure zones in the network. So low pressure zones must be avoided. Now the temperature is not constant in a district heating network, and the piping will become very long. Even small changes in temperature will finally have quite big consequences. Elongations and contractions must be allowed to take place in a controlled manner. Modern prefabricated district heating tubes will, whether twin tubes or single tubes, most often have margins built into them. There may, for example, be thin air slots around the inner tube or an elasticity in the insulation so that the inner tube may move a little from side to side. In a twin tube, will the lengths of the forward inner tube and the return inner tube become unequal because they have different temperatures. The forward tube will become longer than the return tube, but they will both have increased their length more than the casing has. So twin tubes are common in the smaller dimensions, like the connections to the individual customers. In single tubes will the relation between the inner tube length and the casing become different if the tube is placed in the forward pipe or in the return pipe. So the connections between prefabricated tubes is in itself a challenge, and there will always have to be measures taken to compensate for these movements. So everything moves in the distribution system, except two things: the outlet from the main distribution pump and the inlets to the customer heat exchangers and to the substations. These more or less continuous movements will ultimately lead to fatigue fractures. You simply have to plan for accidental breakages and leakages. So you need to plan for parallel feeding so that part of the distribution can be turned off but the customers are still supplied. We will mention that again in the next module. Now just one more thing. Before you attempt to start on the last module, go to the home page of the Swiss company Verenum and download the handbook on planning district heating networks, and then scan through the 40 pages in chapters 3 and 4 in that handbook. So that was all for now.